Hello and welcome. My name is Florian Pfaff and I'm from the Intelligent Sensor Actuator Systems Laboratory in Karlsruhe, Germany. In this talk, I'm going to present a grid filter for the hyperhemisphere. This topology is particularly important for estimating orientations since the unit quaternions lie on such a manifold, as we will see later. This is joint work with my colleagues Kai Li and Uwe Hannebeck. We'll begin with a brief motivation about estimation on periodic manifolds. Periodic manifolds is that, as you can see in a circle, if you go around the manifold, you will arrive at the origin again. And there's also high-dimensional versions, such as the hypertorus, where you have multiple ways to go along this, or the hypersphere, which is very different because it does not have a hole. So why is it tricky? If you have two measurements, one at 60 and one at 300 degrees, then taking the normal means would give 180 degrees, which is not what you want. You would want the 0 degrees here. So, and this is not just a theoretic problem. If you got the prior density with a mean at 60 degrees and likelihood with a mean at 300 degrees, then your Kalman filter will give you something with a mean at 180 degrees. However, this is not a problem of Bayes formula. If you apply Bayes formula, you will get something that has its mean, circular mean in this case, at 0 degrees. So where are the research questions? For the circle, we've presented filters that are very good, and also for the hypertorus that are maybe slow for high dimension, but they work, and also the hypersphere. Then for quaternions, they lie on S3, so actually you can use them already with some filters for the hypersphere. However, Q and minus Q describe the same rotation. And the densities, to be really valid, they have to be symmetric on S3. So if I visualize this on S2, because S3 is hard to visualize, then we have some symmetric density. And our idea is now to just consider a hyperhemisphere, just to half of that, to have a manifold of minimal size. So let's consider some existing filters. We've got a density here which has 4 modes. You can only see 2 of them, but you can imagine how the other are is based on the symmetry. And if you have a Bingham filter, what I did here was I sampled from this density and then approximated with a Bingham distribution. And in this case, I just got something that has 2 modes. Bingham cannot have some very high probability mass along a great circle, but in this case, we get something that's typical that has 2 modes. We cannot have something that has more than 2 modes. We can consider arbitrary models with some extensions. We have a density and we ensure the symmetry, but it can be slow if you use these extensions. Then there's the particle filter, which does not yield a density. You can use any model, you can have any number of modes, and the symmetry is not inherently ensured. You would have to do an extension for that, and the runtime can be very bad if you really want to be precise. Then there's the hyperspherical grid filter, which I've mentioned before, which gives you a density. You can use it for arbitrary models with an arbitrary number of modes, but it does not enforce the symmetry. And this is the point we're going to tackle to further improve the runtime and the precision of the filter. To provide a grid filter, we have to specify the interpretation of the grid values. One is that they encode the probability masses in all the regions. We can get these very expensively via an integral. And the second interpretation is that there are the function values of the continuous density at the grid points. While the grid points are not relevant here, they are obviously relevant here. And we can have an equiangular or more homogeneous grid. And I encode the function values of the grid values according to the size of the circles. And if we now increase the density here, then we'll get with an equiangular grid, we are denser towards the poles than with a homogeneous grid. So, but how can we get to a grid for hyperhemispheres? Our grid generation scheme for hyperhemispheres is based on the zonal equal area partitioning by Leopardi. We're not going to go into details on this algorithm and instead just have a rough explanation that shows the basic idea of our change. If we specify one axis, for example, the z-axis in this representation, that along which we subdivide, we can get all these angles that incur an equal area subdivision using a closed form formula. Then the idea is that we can join some of these and then subdivide one dimension down. So we join many of these and then subdivide them. We join then also these, subdivide them, and join these. And then what we get is we have a subdivision along both the elevation and the azimuth angle. However, the problem here is that if we now only consider a hemisphere, we will get areas, we will get regions that are not of the same size as the other region, since we slice it in half here and the center of these regions is going to move upwards. So the regions are different size, which is something that we do not want, especially for the prediction step that we'll get to later. So what do we do instead is that, well, we just join regions on the upper hemisphere. And then we get something that has equally sized regions. If we now want to do an interpolation, then we can mirror them all onto the other hemisphere. So while our filter never requires us to interpolate the density, it can be very useful to be able to. So for one, we can say that it's piecewise constant in every region. This will yield us something like that, that's pretty coarse. Or we can, for example, for S2 say we mirror it onto the other half of the sphere. Then we interpolate it using some smooth interpolation using spherical harmonics, as you can see here, and then just consider the upper hemisphere to have interpolation for the hyperhemisphere. Let's get to the implementation of Bayes' formula. We've got the grid values shown here according to the size of the circles of the prior density, which to visualize this is interpolated looks like that. And then we need the likelihood evaluated at the same grid points. Here also an interpolation that we'll never really need in practice. And then if we multiply them, we get the grid values of the unnormalized posterior density. Obviously, the non-negativity is maintained here because we just multiply non-negative values, and it's proportional to the true function values. What you have to keep in mind, however, is that if the density becomes more concentrated, then even if the likelihood is considered perfectly by the grid values, then you will lose some information here. This is like in the Fourier series. If you multiply two Fourier series with a specific number of coefficients, then you will need more Fourier coefficients to represent the multiplication result exactly. So you'll lose this increase in the complexity of the density. So let's get to the prediction step, and I'll briefly give the key ideas based on the one-dimensional case because it's much easier to visualize there. So we've got that posterior density from the last update step. It's just depending on one variable, but let's just say this is dependent on two variables. There's another variable of that future time step that our function is currently invariant under. And then we've got the transition density that is both variant on the current and the next time step. Then what this is here, this is just like a joint density that we obtain if we multiply these two functions. All we have to then do is perform this last step, the marginalization, to obtain the predicted density for the next time step. So far, we've mainly visualized S2 spheres, but in our evaluation, we consider the S3 sphere, which is useful for estimating unit quaternions. We see the errors here and the runtimes per time step here for all of the filters. And we see we are more accurate than the particle filter. The particle filter is here, and here's our hyperhemispherical grid filter. And if we use as many grid points as the particle filter uses particles, we are more accurate. And we're also faster. While our increase in runtime is quadratic, the particle filter is actually linear, but the operations it does, the sampling from the density is actually so much more expensive than this highly optimized operation that we have in the hyperhemispherical grid filter, which is matrix vector multiplication, that our filter is both more accurate and faster. It's useful to consider the symmetry because the hyperspherical grid filter, which does not consider the symmetry, needs more grid points to achieve a comparable accuracy, so it's also slower for the same quality. And for S3, it's faster than the Bingham filter in our evaluation. We see we reach a quality that's even better than the Bingham filter here, and we're still below the runtime of the Bingham filter. So, as a summary, we've presented a filter that is very fast and versatile, and we always have a valid continuous PDF via an interpolation, and it makes better use of the grid points than the hyperspherical grid filter. So, as an outlook, we may consider hyperspherical harmonics to interpolate even higher dimensional grids. We may use adaptive grids, which are not as homogeneous but centered around some point at which we believe is more probability mass. There are actually many ways. We've already considered ones with just 2 modes. We may consider ones with more modes. And finally, to derive a Rao-Black equalized filter for AC3 estimation, which combines both the orientation of an object and its position. So thank you for your attention. I'll be happy to take your questions in the Q&A sessions.